a pottery wheel. A small rubber wheel is used to drive a large pottery wheel, and they are mounted so that their circular edges touch. The small wheel has a radius of 2 centimeters and accelerates at a rate of 7.2 radians per second squared, and it is in contact with the pottery wheel, which has a radius of 25 centimeters, without slipping. Calculate A, the angular acceleration of the pottery wheel, and B, the time it takes the pottery wheel to reach its required speed of 65 RPM. Now this is a problem you can sink your teeth into. Let's begin by sketching a diagram of this situation. I have two wheels that are in contact with each other. Now one of these objects is going to begin to spin up and drive the other one. What is it about these two objects that is the same? If the two wheels roll without slipping, then what I'm going to suggest is that it is this tangential speed that's the same in these two wheels. Understanding this point, that the tangential or linear speed is the same for both wheels, is the key to solving this problem, because what I can say then is that the tangential speed for the large wheel is equal to the tangential speed of the small wheel. Well, what that means is that R large times omega large is going to be equal to R small times omega small. If I were to divide both of these equations by time, then what I would see is that omega divided by time, or delta omega delta t, for the large and small would then turn into angular accelerations, and delta omega delta t is the angular acceleration. So now we're trying to figure out what is the angular acceleration of the large wheel, the pottery wheel. So let's divide both sides by the radius of the large wheel, and now we can put in the numbers. I get that the angular acceleration of the large wheel is just over half a radian per second squared. That's part A. Now let's go on to part B. We're trying to find out the time it takes for the pottery wheel to reach its required speed of 65 revolutions per minute. That 65 RPMs is essentially an angular speed. Let me convert that revolutions per minute into radians per second so that we can use one of our radian equations of motions. I get that when I convert radians to revolutions and minutes to second, that the final angular speed is 6.81 radians per second. So now my initial angular speed is 0 because I'm starting from rest. Let's use the equation of motion, that first one that relates initial, final, and acceleration. Our initial angular velocity is 0, and I'm trying to figure out what the time is. So I want to solve that equation for the time. The time is going to be the final angular speed divided by the angular acceleration. And this is for the pottery wheel, so we're talking about the large angular acceleration. Now I can just put in the numbers. And I get that the final time, the amount of time it takes to get it up to 65 RPMs, is just under 12 seconds. Here's another example. For a bicycle, how is the angular speed of the rear wheel, omega rear, related to that of the pedals and the front sprocket, omega front? That is, derive a formula for omega rear divided by omega front. And there's a hint. Let N front and N rear be the number of teeth on the front and rear sprockets, respectively. The teeth are spaced equally on all sprockets so that the chain meshes properly. Then, in another part of the problem, we're to evaluate the ratio omega rear divided by omega front when the front and rear sprockets have 52 and 13 teeth, the largest front sprocket and the smallest rear sprocket, that's basically high gear, and in part C, when they have 32 and 35 teeth, when the smallest sprocket and the smallest front sprocket and the largest rear sprocket, which is low gear for climbing hills. There's a picture here that shows what's going on. And what I would suggest to you is that just in the last problem, the thing that's going to be the same for both front and rear sprockets is the tangential speed, because the chain is what is connecting those two things together, and the chain is traveling tangent to the circle. Your diagram even hints at this by showing this speed of the chain, and the chain going around the tangent to the circle both in the rear and in the front is what is going to be the same. So now we're trying to figure out this ratio, omega rear divided by omega front. Since the tangential speed is the same for front and rear, then we can relate some other quantities to each other. V is equal to R times omega. In our diagram, the radius of the front wheel is this R front up here, and the radius of the rear wheel is this R rear that's back there. Let me change my lowercase letters to uppercase letters to indicate that. Now, how can I relate these radii to the number of teeth that are on the sprocket? Well, let's think about what the sprocket looks like. If I think of the sprocket as a circle, and let n be the number of teeth that's around that circle, then I can relate the number to the perimeter. In other words, n teeth is equal to 1 circumference. But what is the circumference? It's 2 pi times the radius. So I can write that n teeth is equal to 2 pi times r. So that means that r is basically going to be n divided by 2 pi. Let's feed that into our relationship that relates the tangential speeds to each other. Tangential speed equation becomes that the number of teeth divided by 2 pi times omega front, this is in the front, is equal to n rear divided by 2 pi times omega rear. The 2 pi's are going to go, and now I have a relationship that I can put into a ratio. Let's put that together. I have a relationship that says the ratio of the angular speeds is going to be equal to the ratio of the number of teeth. But notice where the subscripts are. Omega rear divided by omega front is equal to n front divided by n rear. So what does this mean? What this means is that the number of turns, if you want to think about it, in the front and the number of turns of the wheel in the rear are going to be related by these teeth ratio. Let's evaluate that for the numbers that they have. Part B. What we have in the B part is essentially high gear. So now let's put in the numbers. And I get that the angular speed of the rear wheel is going to be 4 times the angular speed of the pedal. So when you go one time around in the front with your crankset, then the rear wheel is going to spin 4 times. That's what we call high gear. When you travel down a hill, then you end up with a large wheel speed compared to the front sprocket speed. Now let's do it for low gear, climbing a hill. So let's feed these numbers into our equation. What I come up with is that the rear wheel will spin just over 9/10 of a turn when the pedals are turned once around. This is a very low gear, and it gives you a lot of torque, which will allow you to climb a hill. So there's a practical application in terms of bicycles. One more. Here's the last example. A cyclist accelerates from rest at a rate of 1 meter per second squared. How fast will a point on the rim of the tire, which has a diameter of 68 centimeters at the top, be moving after 3 seconds? And the hint is, at any moment the lowest point on the tire is in contact with the ground and is at rest. I want to take a snapshot of this picture. At the instant during which the tire is moving at 3 seconds. And I want you to imagine that I have myself here a large circle that has a point that's at a radius of half of the diameter of the tire and a point that's the whole diameter of the tire. In other words, you could think about this whole tire basically spinning around an axis, and at the instant in question, the center of this circle is the point that's momentarily at rest. The acceleration that I know, the linear acceleration of 1 meter per second squared, is happening at the middle of this radius vector, and the point that I'm interested in is at the edge of this radius vector here. If I could find out how fast the center of the tire is moving after 3 seconds in linear speed, then I'll know that the top is going to be moving twice that fast, because the top of the wheel is twice the distance away from the ground as the bottom of the wheel. So let's figure out from a linear equation of motion how fast the center of the wheel is moving after 3 seconds. And to do that, I'm going to use a linear equation of motion. Now I know what the acceleration of the center of the wheel is. It's 1 meter per second squared. If I am starting from rest, in other words, I'm starting off when I'm not moving at all, then I can figure out what the speed of the center of the wheel is. I can just put in the numbers. And what I get is that the center of the wheel is going to be moving at 3 meters per second. Now what about the point that's at the edge of the wheel? Well, again, if I notice that the edge of the wheel essentially is twice as far from the point on the ground as the center of the wheel is, then the edge of the wheel is going to be moving at 6 meters per second. And in fact, it doesn't matter what the radius of the wheel is. If the center of the wheel is moving at a certain speed, the top edge of the wheel is going to be moving at twice that speed. So, in this lesson, what we have done is we have related angular motion and linear motion together. When the object's moving in a circle, there will always be centripetal acceleration, even if there is no angular acceleration. On the other hand, when an object changes its angular motion, changes its tangential motion, then not only is there centripetal acceleration, but there's also angular acceleration. And we've now developed the tools to deal with that angular acceleration and solve some numerical problems. So, for now, that's it.